Thanks for the invite. It's a pleasure to speak in this seminar. Actually, over the past few years, I've been watching a lot of the videos at my own pace. So that's great of this new form of presenting. The downside, of course, is that there's no live audience, but please feel free to interrupt me if you have any questions. I'm fine with that. So the topic is a fairly new topic I've been working on with a colleague in Tilburg, Pieter Kleer. And it's actually about a very basic optimal stopping problem. So let me start with explaining the problem in quite a bit of detail. And then I'll explain what we added to that topic. So it's an optimal stopping problem where there's a seller who has one product, one item up for sale, and there's buyers arriving sequentially over time, and each buyer has a certain valuation. So denoted by VI, the value of buyer I for that one item. And these values or the offers of the buyers are revealed one at a time. So the seller needs to decide whether to select a certain offer I or reject it and wait for future offers that might be better. So like I said, a very classical traditional setting. And well, the goal would be, one goal would be that the seller, in this case, select the best buyer in terms of maximizing the value for that one item. So this is clearly a process that has a component of time. So if you look at the picture, the horizontal axis, this is time or the buyers that arrive sequentially. And the offer could still be too low, so the seller rejects that offer. Perhaps this is the offer that the seller would accept. And then, of course, future offers might have been higher, but somehow the seller decided to go for the third offer. This raises the question, what type of rules should the seller use in order to have a good stopping criterion? And clearly, if the seller would be a prophet and would knew all future offers, there's no interesting question to ask. So we'll first look at let's say, classical setting of knowing at least something about the future offers. And what people typically do is what we call the Bayesian approach, where the seller knows the distribution of the future offers or the buyer's valuation. I'm going to denote these priors by P1 up till Pn. And in principle, all distributions are allowed in this setting. And you should interpret now the value Vi, so the offer I, as an outcome of that distribution. So there's a random variable xi representing the value of buyer I. It has a certain distribution, and the outcome is what you see as a seller. And of course, you want to develop a strategy that anticipates knowing these priors. So that's the Bayesian framework. And the only thing I'm going to assume is that these distributions are independent, which means that the buyers do not synchronize, or there's no they're just independent actors in this game. So here's a little example that helps, I guess. At least it helps me in visualizing what's going on. So these are 4 buyers. They all have a uniform prior. Notice that the prior might be different, but independent. And then, to play this, the actual game, the seller would need to see a value, and that would be then a sample from the uniform distribution in this case. So in this way, you would generate multiple values. And the question is which offer, which value to take, where to stop. So in a bit more formal language, we're looking for some rule, the stopping rule, we denote it by tau, that would maximize, in this case, the expected payoff, which would be the maximal value that you could select. And as you see, I'm going to denote this expectation by E of x tau, where x tau is the box in the picture that you select. And in this setting, of course, it depends on all the priors. So that's why they're in the index. And somehow the rules should optimize this objective. You could take alternative objectives, but this is the setting we're going to work with. So I hope the setting is clear. I'm sure all of you have seen this example before in this form, or perhaps a slightly different form. So it's classical, and in a minute I'll tell you what our take on it is. But this is a fairly general way of approaching this problem. Okay, so for now, think of the stopping rule as a deterministic rule. You could also look at all different types of rules, more randomized rules, but I'm not going into that direction. I'm going to show you, and again, I'm sure a lot of you have seen this, the way to derive the optimal stopping rule in this Bayesian setting. It's really textbook material. So we're going to use backward induction. At the very end, when there's only one offer left, buyer n, if the value distribution is non-negative, we're going to accept that offer. That's the best we could do at that once we've reached that stage. Even if it's not a good offer, we're going to select it. So that's the starting point, let's say. And now we go back in time, and let's say that two offers left, buyer n-1 and n. Then we're going to select offer n-1 if that value, that offer, is high enough. And in fact, we'll accept that offer if it exceeds the expected payoff at that point in time. And the expected payoff, if we would not accept that offer, is really the final buyer. So this is a criterion that makes sense, a stopping rule that makes sense. Now, if you keep reasoning like this and you go further back in time, the same type of reasoning could keep applying. So shorthand notation, that expectation of time point n-1, I'm going to denote it by tn-1. It's going to be a threshold, that's why. In this way, I could keep identifying thresholds. So for instance, if I'm at point n-2, so there's 3 buyers left, I'm gonna take that offer if that offer exceeds the expected payoff from the 2 buyers that are still to come. So that's what you see here. So in this way, I gradually build a whole set of thresholds by going backwards in time, so backwards induction. And I hope you get familiar with the notation T sub n, which is the notation that I'll keep using. And in fact, it's a threshold, but it's also an expectation. Okay, so yeah, if you keep arguing like this, then this is the textbook result saying that you will select offer I if offer I exceeds a threshold Ti, where Ti is really the expected payoff of everything that will play out in the future. That's the way to interpret it. And the reason why this works, one of the reasons is that, yeah, because of expectations, obviously, but also that we have a nice starting point at the very end. So the threshold with buyer n is clearly 0. And in this way, you could keep going backwards and find the thresholds. So if you're in the Bayesian setting and you would know all the prior distributions, then you could calculate this whole sequence of thresholds. And in fact, you have an explicit stopping rule. So the rules that the seller can use to make the right decision. Okay, so the threshold Ti, remember, is the expected payoff obtained from I plus 1 onwards. And I'm also going to use the notation T0 for the expected payoff of the entire selling gain. And that's one of the things, of course, you want to get as high as possible. Okay, so this is our starting point. And let's go back to the little example once more. so you do see you see the four buyers. We have prior distribution to uniforms. Before we already sampled from the distribution. So this is the V1 up to V4. Those are actual numbers. But now we can also calculate the thresholds, which would start at buyer 4. We will always accept that offer. So there the threshold is 0. The threshold at buyer 3 would be the expectation of X4 X sheet, so that's 6. And then we get some non-trivial numbers by going backward in time. And in fact, you could also calculate T0 in this case, which would be the expected payoff if you would live by this rule. And the rule would be that the red thresholds, they're fixed. And whenever this game plays out, and the moment one of these valuations exceeds some threshold, you stop. And if you would do this infinitely many times, this is the expected payoff that you can count on. Yeah, so that's the setting. Okay, and this observation is really the consequence of the Bayesian setting. So if you have full knowledge of distributions, you can calculate the thresholds. And we want to relax this observation of this assumption, let's say. Well, not per se because it's unrealistic in practice, but you might argue that knowing real old detailed priors, that's quite a heavy assumption. But we also want to look for a bit more robust statements that do not need like the full specification of all the distributions. The red numbers that you see here, they need all that information. And the talk really is about, we're getting there, what the goal of the talk is, but it's really about relaxing that assumption. And we're going to take a distributionally robust perspective. So how does it work? We'll keep thinking in terms of a stochastic model. So this is a stochastic model because there's a whole bunch of distributions involved. But instead of having a very detailed specification of the priors, we want to work with only partial knowledge of those distributions. And we're going to allow for all sorts of limited information, but the main example I'm going to show you is really when you know the first two moments of the distributions, for instance. So that's limited information on the one hand, because it limits you because you know not as much as when you would know the full distributions. But on the other hand, it also gives you a more robust way of stopping, because the rule that you probably will identify would work in some way for all distributions that have that comply with this, for instance, the first two moments or whatever information that you have. So that's the setting. Here's the main example. And formally what we'll do is once you know for buyer I, the mean mu I and the variance sigma I squared, and you would say this is the only information that you know, and apart from that, everything is possible. We're going to build an ambiguity set. That's a standard notion in distribution robust optimization, and it says that this is simply the set of all measures P that have the same mean and variance. So the information is used to build a set of allowed distributions, and every buyer can have its own ambiguity set. Okay, and now instead of a Bayesian approach, we're going to switch, which is a very natural switch, to a max-min game between the seller and the adversarial, and I'm going to refer to that as nature. So how would it work? The seller chooses some stopping rule, tau, as before, but then the nature gets the chance to choose the distributions as bad as possible. So we're looking for a worst case scenario. So the seller tries to maximize the payoff, and nature tries to minimize that payoff by actually selecting the distributions in the ambiguity sets that are worst case. So that's you could see that as a game between seller and nature. And then the goal would be to find still some optimal stopping rule, optimal in this case, that maximizes the robust expected payoff, which would be the max over all rules and the min over all distributions that comply with the partial information. So the max is the seller and the min is nature, and the objective is still the same. I'm going to speed up a bit because I think I'm otherwise going a bit too slowly. And again, please interrupt me if you have any questions. Okay, so this is the goal. Just copied it from the previous slide. And I'm not going to mention a lot of references. We do mention a lot of references in our archive papers, so please check there. I just want to stress that this elementary setting that we now look at, of course, has connections with various fields and is studied a lot in various ways. So first, stopping theory and online selection, that's a very big topic with many papers. So it's part of that area. Actually, one of the most elementary examples of that area. The reason why we got into it really is that we do quite a bit of research on distributionally robust optimization. So that's the max-min and max-min in a way that you preserve the distributions. So that's why it's distributionally robust. And I'll also give you a few pointers to some other recent research that we've been doing in our group at the end of the talk. So that was really our main focus. And obviously, we went through the backwards induction. There's also a clear link with dynamic programming. And in fact, there's a lot of work out there on robust dynamic programming as well. So yeah, I just want to mention that it's an example that connects various fields, but it means that there's also a lot of work out there to explore, obviously. Now, so the first result in the paper is actually connected to all these branches. So we come up with a standalone proof, but it's definitely related to some other notions out there. But let me first tell you the results. So indeed, you could, when you take this max-min perspective, you could identify still stopping rules that are then robust and tell you that you're gonna stop whenever the value is bigger than the threshold Ti. And in this case, the threshold Ti is almost the same thing as we've seen before, except that nature gets a chance to make this as bad as possible. So you see the red part here, which, so this is something we would like to optimize as a seller, and nature gets a chance to make this worse, or the worst case in the ambiguity set. So this is then something that we need to resolve in order to identify the threshold. So it's no longer an expectation that we can calculate with the distributions, but we really need to look for the worst case distribution. Yeah. So we found actually many papers that do related things, but typically in a much more general setting. So here I mentioned a few papers that have a similar result. To be honest, not the exact same result, but please check in our paper for some reflections and references. A few more things, and then I'll return to this theorem, because this is the starting points, let's say, of our paper, and then we will try to identify these stopping rules in closed form. But before I go there, let me mention that we also proved that max-min is min-max. So yeah, the order of play is really not important. You could first let the seller choose a rule, and then nature look for the extreme scenario, or the other way around. Doesn't matter in this case. The ambiguity can include moments. I'll focus on moment problems, to be honest, but definitely you could include more information if you like skewness or tail probabilities. Yeah, or you go for a completely different type of ambiguity, like once you fix a reference distribution and some distance measure, like phi divergence. Yeah, this is also allowed, but it's a completely different challenge then when you want to identify the threshold. So that I leave for future work, but starting from the same theorem, you could, yeah, in principle, as long as it's independent, you could substitute any ambiguity set you like. And then the calculations that are that you're facing will very much depend, of course, on the choice that you make for these ambiguity sets. The most important reference is the Boshuizen-Hill paper that we found when we were studying this problem, and they in fact analyzed in detail the mean variance case of the result I just showed you. So the result I just showed you is general, but they focused on mean variance and have a result that actually I'm gonna derive with a new proof in a minute. So I can tell you what it is exactly that they proved. And the way I'm going to derive that result is a method that we've been using in various projects lately, Primal-dual method. And we've learned that method actually from the original SCARF paper for the robust news vendor problem. You might have heard about that result. So I hope you like that Primal-dual method. Yeah, one of the goals of this talk, in the time that is left actually, is to show you that Primal-dual method in quite a bit of detail, and also try to argue why it might work in other cases as well. Okay, a few more references. Of course, you could also have other types of limited information. For instance, people have studied the same problem, but then let's say they say that they know the distribution, like it's a uniform, but they don't know the parameters. So that's a setting you could study. And to mention another interesting paper recently of Goldenstruger and Zevi, who study also the IID setting, so the exact same setting, but there they don't know anything about the distribution, and they try to build up stopping rules starting from there. So many possible angles, and we take our own specific angle on this problem. Okay, so this is what we need to solve, remember, again, copied from a previous slide. And to be a bit more specific about what we now want to do next is that we want to solve a problem like this in closed form. So for instance, for mean variance information, can we identify the threshold TI in a closed form or in a form that's at least explicit? And whether or not we can do that, this is one of the takeaways probably, will depend obviously on the ambiguity set. So the choice of information that you make will heavily affect whether or not this is a tractable problem or not. Although, of course, numerically you could do all kinds of things, but we've not focused on that. So the main example I start with is identical mean variance ambiguity. So identical in the sense that every buyer has the same distribution or the same ambiguity set. And we know the mean and the variance, and apart from that, it could be any distribution. And the goal now is to determine the thresholds Ti, and hopefully as explicit functions of the mean and the variance. That's the information that we have. And of course, also as a function of the number of buyers n. That's a parameter as well in this problem. To realize that we need a certain limited amount of information, let's take a wider ambiguity set. So all distributions that have a given mean mu. So in this case, the seller would immediately accept the first offer. So would have an expected payoff of mu, because nature could simply, as a worst case scenario, take 1-point distributions with mass on mu, and there's nothing more to gain it's the end of the game, let's say. So it's a trivial degenerate outcome. So yeah, the thresholds will all be equal to mu, and there's nothing more really interesting to say about it. Now, perhaps a bit surprisingly, if you go for the ambiguity set I just introduced, the result is still trivial. It's a bit harder to see, but it's important to realize why it's trivial. So the same outcome still is there. And I'm going to explain this to you by arguing that somehow if the range of the value is infinite, then it's a trivial problem. And yeah, the best thing for me to explain this is by going to two-point distribution. So I hope you see this sub 2 here. So it means that I'm restricting the ambiguity set even further by only allowing two-point distributions. I'll relax that in a minute again, but the good thing about two-point distributions is that I could immediately, well, I only have 2 points, and I can immediately choose the points and the probabilities such that I have mean mu and variance sigma squared. And yeah, then I'm gonna calculate these thresholds. And yeah, if you look at these A and B choices, you could argue, it's a bit subtle, but you could argue that all these thresholds would still be equal to mu. And the best way to understand that is that I can let P go to 1, right? And if I do that, then yeah, this is what we see quite often, that so now I will have value A with a pretty large probability, and a value B, which becomes a very large value with a small probability. And if I push that to the extreme, I end up again with, yeah, you could say nothing, with thresholds all equal to mu. And it also shows you this example that if I don't restrict the range, then I get a degenerate result. Yeah, so that's for us, this was an important motivation, because that's why we chose to work with this ambiguity set. So it's the same ambiguity set as before, so mu sigma squared, but now the range is restricted to capital L. Yeah, so that's a finite support, let's say 0L. Yeah, one step I did not explain in detail, but remember I'm solving that min-max problem for the thresholds, and I simply rewrote it here into a max-min problem. Yeah, if you go through the analysis slowly or quickly, actually, you could see that this is equivalent. And I did this because I like this formulation a bit better. So we're going to solve the max min here, and that's the goal under the ambiguity mu sigma squared L. So let's go and try to do that. And yeah, there might be other ways to approach this problem, but yeah, we really like to view this as a semi-infinite LP, and it would look like this. So try to find, let's say, the bound on this integral by looking for all allowed distributions, pi plus 1, and build in 3 constraints. It needs to be a distribution, that's constraint 1. The mean was given and the variance was given. So 3 constraints. Why is it called semi-infinite? It's a linear program, but we're searching in this ambiguity set, which has infinitely many possibilities. So it's nice that we have only 3 constraints. That will definitely help us in solving this problem. But it's still there's still a lot of possible maximizes. And yeah, it's actually these semi-infinite LPs, they pop up a lot in distribution robust optimization. So many papers out there study versions of these type of problems. On the other hand, they are a bit special. And so for instance, we're gonna apply Primal-dual methods, standard methods, to solve this problem. But the fact that this is a semi-infinite LP, and in particular that it has 3 constraints, will definitely help us in getting a really nice solution to the dual problem. So I'm going to show that to you next. But I hope the problem is clear. Yeah. So where did we came from? We were looking for thresholds. The thresholds in a robust setting need to solve this game between seller and nature. And that game we now translated into a semi-infinite LP. And this one in particular will have a really nice solution. This is what I'm going to show next. So we're going to switch to the dual program. So how did this go? It's a standard procedure. From the maximization problem, we go to a minimization problem, looking for 3 variables lambda that together have this objective And now the constraint is that there's a function here. This is a nice parabolic function that needs to be bigger than the original objective function. So this is the dual program of the primal on the previous slide. And what is special about it is that this now, because of the three constraints, is a nice, nice, easy polynomial. And that structure we will try to exploit. So let's visualize the problem here. In this picture, you see the minimum, that function here. And by the way, the threshold is really just a number here. Right? It's you could fill out any constant. It's just a constant. And then this parabola here, that's the dashed line. Yeah, you could draw it as you like, as long as it's above the minimum function, the objective function. But on the other hand, if you look at a minimization problem like this, it's quite likely that you're looking for the tightest, let's call this majorant. So the function that's just above that function. And because this is a piecewise linear function and this is a quadratic function, yeah, you could let it touch that function in 3 points. This is going to be an important, actually, insight. That's just, yeah, a visual insight at this stage. But if you would apply complementary slackness, for instance, you could argue that the worst case distribution, the one that solves this problem, is supported on these 3 points, because yeah, due to complementary slackness, this has to be the case. So yeah, that really constrained, yeah, that makes life much easier, because now instead of searching the entire ambiguity set, we only need to consider 3-point distributions, which is, by the way, something we knew up front. For these type of semi-infinite LPs with 3 constraints, we know that we need to look for 3-point distributions. At least among the optimizers, there will be 3-point distributions, to be specific. But okay, so how would you then complete a proof having this insight? Because this is of course a very valuable insight. We would go back to the primal problem. So these 3 steps I'll demonstrate twice. So what we do is the dual solution will give a candidate for the worst case distribution, but of course it's a dual, so it's there could still be weak duality. It's an upper bound, but we don't know if it's a tight bound. But because the candidate is identified, we go back to the primal problem. Then with these 3 points, try to solve that problem. And then if we get the same objective value, there's strong duality and we have the tight bound. So that's something, of course, that also works in much more generality, but here we do it with all the specific information that we have. So how would this work? So first, before I go back to the primal, that dashed parabola, yeah, that needs to be fitted. So I need to choose my lambda 0, 1, and 2 such that it is the fitting tightest majorant. So as it happens, these then should be the parameters, and the dual objective is this value. So I hope you see what I've just done. Nothing really then interpreting the picture. And then I go back to the primal problem, and I know upfront, due to complementary slackness, that I need to construct a 3-point distribution on 0 xi and L, where, by the way, I've replaced ti plus 1 by some number xi, because it's really just a number. So that, yeah, there's one unique solution that does this, because I have, of course, the constraints of mean and variance. And then if I fill out that 3-point distribution in the primal objective value, I get the same value, which means that I found the optimal solution. Now, there are a few details. In the interest of time, I'm going to skip those, but let me, without going through the details, let me explain this to you. So I just created the 3-point distribution, but these probabilities, of course, should all be in between 0 and 1 and add up to 1. And it's only, it's violated when the constant xi is outside this interval. For solving the threshold problem, I only need this interval, by the way, but if you're outside that interval with the same type of reasoning, you could also find the tight bound, but they're a bit trivial. Taken together, you find a result like this. And this was already proven by in a paper by Cox in '91, not with the Primal-dual method actually, but you can find this result in that paper. And here the middle interval, that's the one that we need for our purposes today. And here you see also these other two cases. This is a bit cryptic, by the way. So we're looking for the max of the min. What this essentially says is we're looking for the tight bound, the sharpest possible bound of the expectation of the minimum of some constant psi and capital X, where X is any distribution with given mean, variance, and support. That's what it says. Okay, so this middle region, that's the result that I need. And now, remember, I was trying to calculate these ti plus 1s in a recursive fashion. And if you plug in this result here, in that recursion, you get a really nice affine relation. And you can solve that in closed form. So this, in fact, was the result of Boshuysen and Hill. And it's an explicit formula in the actually four system parameters, mu, sigma, L, and N. And you also see that it's a decreasing function. So in the beginning, the thresholds are a bit lower than in the end, and that all makes sense, I guess, because in the beginning you're willing to take a bit more risk in the hope of getting a higher payoff. And it's all tight, so you cannot do better than this, because in the max-min problem we found the exact solution, so that this is the optimal robust threshold that you could work with. If you actually let n go to infinity, you also see that the expected robust payoff is mu plus sigma squared over mu. So it's non-degenerate, it's higher than mu, and actually you would benefit from more uncertainty sigma in this case. And there are all kinds of interesting insights, of course, to explore further, but I want to focus mostly on these type of main results. Okay, now this is a picture that deserves some explanation. So this is an example of 20 buyers, and yeah, what you see here are actually the 3-point distributions, the worst case distribution that we've identified with the Primal-dual method. But for every point in time, we have a different worst case distribution. So if you play this game at the very end of the time horizon, you as a seller are still facing a 3-point distribution, as always, played by nature, let's say. But look what happens when we go back in time. So there are the three values, 0, ti plus 1, and L. L, remember, is the largest possible value. And then when we go back in time, that largest possible value no longer seems to play an important role. And also the other two values, so 0 or some non-trivial value, they seem to be dominating this game. So the game really goes from a 3-point distribution to a 2-point distribution. And this is something that we felt was interesting from the start, because we felt that nature will probably play an all or nothing game, so creating a scenario where either you get nothing or the highest possible value, let's say. But you also see that the range, the max value does play a role, and we need that max value, remember, because otherwise we have a trivial problem. So yeah, remember that this observation for the last part of the presentation, because the other examples I'm going to show you will also be about all or nothing scenarios. And here in the beginning, it's a more complicated picture, but certainly when there's enough time, you're facing an all or nothing scenario played by nature. I'll get back to that, but at least numerically, you could convince yourself based on this picture that here this is also the case. So it's not really the 3-point distribution that we're facing that comes from this semi-infinite LP reasoning, but you could argue in many situations it's a 2-point distribution. And yeah, we felt it's interesting, but it also might have a deeper meaning, because here you're facing a completely different worst case scenario than here. But well, if time permits, we could speculate a bit about that, but it also has some probabilistic intuition. Okay, anyway, the takeaway from this picture is that if we go back in time, or if there's enough time ahead of us, the worst case is really, yeah, nothing or the only possible other value with unique probabilities. Now, the next form of ambiguity that I want to show you is almost the same setting, except we're going to trade or replace the variance by the mean absolute deviation. And this is not a coincidence that we look at this ambiguity set, because it plays, it's been utilized in DRO quite often, because mean absolute deviation has some nice properties when it comes to semi-infinite LPs, but also when it comes to being more robust to larger values. And what is a bit weird about the mean variance example is that it's so depending on having this capital L. If we don't restrict the range, then things become degenerate. And as you'll see in this case, L will not play a role. So that's one reason to take mean absolute deviation. But I'm going to give you a more compelling reason, because the Primal-dual method will work really nicely here as well. I'm not sure how long it's been that you've seen the mean absolute deviation. Before we started working in this line of work a few years ago, I'd never used it in my own research, but the more you think about it, yeah, mean absolute deviation is not that different from variance, except you're not penalizing the extreme values that much as variance does, but it's a dispersion measure like variance or any other measure. But again, mathematically in the DRO context, it has some really favorable properties, but okay. Now, I'm not gonna restate the primal problem. Let's go back immediately to the dual problem. So how does the dual now look like? It's almost the same objective, except that here's now a value for mean absolute deviation, and there was the variance before. And the main difference now is that here, instead of an x squared, which had to do with the variance, we have the mu minus x, which has to do with that function. And it's a piecewise linear function, that left-hand side here. But it could bend only at mu, right? Because if you try to plot this function, it's quite limited. So piecewise linear, and it needs to be wrapped around still the same minimum function. So that's the visual picture here. And then the proof method will be the same. I'm going to call this function now the majorant. I did that before already, but just to stress that this is the function that we need to choose. And we do that, of course, by selecting the parameters lambda 0, 1, and 2. Okay, so I'm going to show you this result, which is the tight bound as before, but now for mean absolute deviation and finite range. And the right-hand side still depends on that finite range, but this is the result that I'm going to use. The rest I don't need. There's a lot of notation here, so let's go through the proof and then perhaps return to the lemma. So here's the picture. So we still have this minimum function, and now we have very limited choice for constructing the dashed function, the majorant. And this seems to be a sensible choice. At this point, it could still be a bit of guessing, because it's yeah, it's on this minimum function for this part, and here there's a bit of a distance, but you could argue that you cannot do much better than that. And some other candidate could be this this flat line here. But let's first focus on this one. So if I want to build that function, I need to choose my lambdas like this, and the dual objective would be this number. You could just check that later, but there's only one way to fit that curve. And then I go, oh yeah, I should perhaps have one more observation. So remember, due to complementary slackness, the worst case distribution needs to have mass on L, for instance, here. But here, the two curves intersect at the entire interval 0 psi. So that means that I could build, yeah, a lot of distributions, because all these points are possible to include due to complementary slackness. But I'm going to keep life easy. I'm going to just say, I'm going to select here 0, psi, and L. But that's not a unique optimizer. The L is, but what I do here, that's more general. So yeah, I hope you bear with me, but I'm just gonna choose these 3 points, although it's not unique. But once I choose these 3 points, I have unique probabilities, of course, due to the limited information. And in this way, I've indeed find the same objective in the primal. So again, I have the tight bounds. Now looking at these probabilities, there are some complications. So again, yeah, the constant psi needs to be bigger than some threshold psi1, otherwise I get negative probabilities. And there's another constraint popping up, this one here, but this should always be the case. It's a natural upper bound on the mean absolute deviation. So there's still some cases left, but at least the first case is settled because I have agreement between primal and dual. And then I go through all the other cases. And unfortunately, now I need to discuss some of these cases, because the first case is not the case that I need. But let's say if you're in this regime, so the constant is smaller than some value psi1, then we try this majorant. And in this case, I could choose a 3-point distribution, for instance, from this part. So for instance, select psi, mu, and L, but again, it will not be unique. And then going through the machinery again gives me the tight bound. And finally, and this is the most important setting, if the psi, the constant, actually the constant is always the threshold, right? But I need to settle this for any constant. If that constant is bigger than mu, and actually we know that all these thresholds, if they're non-degenerate, are bigger than mu. So this is the relevant setting. Yeah, then I'm gonna guess that the dashed majorant is the one that will pull this off. And then I need to include 0 in my 3-point, and I'm gonna select psi and L. So the dashed majorant is given by these lambda values and give me a certain objective value. And oh, am I skipping something? Oh yeah, and then I construct for these 3 points the distribution. And look, this is a quite important observation. So remember that there's no uniqueness here. I go back once more. I'm going to decide to select a point there, 0, and a point here in this interval. And if I do that, I can construct a distribution that has indeed the desired mean mu and mean absolute deviation d. And I'm not utilizing the finite range, which the L, which is something I didn't want in the first place, but if I have to, I will do that, of course. So in this case, in this most important case, I can pull this off with only 2 points instead of 3 points. And again, closing the story by showing that primal is dual. Now, let me now go back once more to the lemma. It's, as before, a tight bound on the expectation of the minimum of a constant and x in a certain ambiguity set. There are 4 cases, and the case that I'm going to use is this one. And then I go back to my recursion for the thresholds Ti and try to solve that recursion. So skipping a few steps, because this is the same recipe, we end up with a result like this. So the optimal threshold now is again a nice closed form solution. But in this case, yeah, it depends not on the parameters mu and d and not on the parameter L. In the interest of time, I need to skip a bit, so I won't show this numerically. But remember, that's the main thing. There's a good bad scenario where this is the worst case scenario played by nature in every step of the game. So that's, yeah, we felt that was interesting. And that's why in our paper, we've also focused on 2-point distributions to start with, but perhaps in the interest of time, I'm going to skip that. Let me explain to you why we started to like this primal-dual method so much, in particular in relation with a mean-mad ambiguity set. So first of all, in this paper of Scarf, which is really a wonderful paper and actually quite a famous result, this primal-dual method is actually applied, but then for the mean variance, and the function of interest is really the max of x and 0, which plays the crucial role in the Nussbender model. So that's where, yeah, you could learn that method. At least it seems to be the first time in the OR literature. We've been mostly focusing on, so I'm going to briefly mention these works, joint work with Wouter van Ekelen and Dick den Hertog on problems that have multiple random variables. So that, of course, in today's problem, there were multiple random variables, but they never entered the function because we have this backward induction, right? So we solve one problem and then go back in time. But we started working on these type of problems, looking at the GG1Q, where, yeah, a long-standing problem is, for instance, to find the tight bound on the expected weight given the mean and variance of inter-arrivals and service times. That problem is still open. A lot of progress has been made, for instance, by Chen and Witt in recent years. And we looked at that problem and considered mean-mad ambiguity instead of mean-variance ambiguity. And then, yeah, the problem is solvable. So the tight bound for the GG1Q is given by 3-point distributions for the inter-arrivals and also for the service times. We've also recently applied that to appointment scheduling, which adds some optimization dimension to that. But the point is that whether you could solve these type of problems, so find tight bounds for expectations of functions, really depends on the combination of the function that you look at, so max functions here, for instance, and of course the ambiguity set with sets which build these constraints in the optimization problem. And for us, in these cases, for instance, mean-mad problems are solvable and the mean-variance counterparts are much harder. So that's very intriguing, but yeah, that deserves a separate presentation, I guess. Recently, we've also been applying the same method, for instance, to a function like this one. So it's a minimum function again, but here you see a product of 2 random variables. So that poses different challenges, but the primal-dual method works. And we also wrote a paper on Chebyshev type bounds, but then for mean-mad ambiguity. So tight bounds for till probabilities, and again with primal-dual reasoning. So I'm gonna wrap up because I had in mind not to use more than an hour, and otherwise Quang would stop me anyway, I think, right? We didn't talk about how long the presentation should be, but I guess 1 hour is max. So a very nice thing that I'm gonna skip now is that we also prove the worst case nature strategy when you start from 2-point distributions right away. And in that case, you cannot use primal-dual method. I can't really explain it now in real time, but you can't. And we have a kind of a separate unorthodox method to prove that. And visually, I could tell you why this is interesting, because remember, this is this example with 20 buyers. And the optimal threshold is likely to go down over time. And now if you restrict to 2-point distributions, then there will be a threshold in time. And after that time, the max value L will play a role, and before that time, it will not. So there's a non-trivial, let's say, transition in time where nature switches from the worst case strategy. But okay, the details can be found in our archive paper. Yeah, this detail definitely I'm gonna skip. So let me wrap up. This talk was really about a stopping problem, an elementary stopping problem, but then our robust max-min take on it. In the end, this was the mathematical challenge. So this came out quite rapidly, actually, from recursive reasoning, but then the actual math game started to solve problems like this. And to do that, I showed you the Primal-dual method for mean variance support. That was a known result. Mean math, and this one I skipped, but it's actually quite nice to read that proof. And kind of a takeaway is that if there's enough time, nature will choose this all or nothing scenario. And for these ambiguity sets, we already knew that it would not be more complicated than 3-point scenarios. But in fact, we feel quite a generic insight is that it's really about 2-point scenarios, all or nothing. And that would be it for today. Thanks.